Let's look now to finish chapter 5. Let's look at section 5.9 and talk about the hyperbolic functions. You're familiar with the circular functions, also called the trigonometric functions, which relate to points on the outer edge of a circle, right? When you have an outer edge of a circle, you have the points along the outer edge of that unit circle relating to the cosine of a value t and the sine of a value t. And you go through that relationship in trigonometry. The hyperbolic functions do something similar. You say, okay, I have, instead of having a circle of radius 1, we're going to have a hyperbola, which is going to be asymptotic to these lines, where this line is x is equal to y, and this is x is equal to negative y. And you're going to have this starting at the point 1, 0, and following these asymptotes this way. And here we only worry about the right half of the hyperbola, not the left half. And just like over here, where each point on the unit circle gives us a pair of functions, the cosine and the sine of some value t, depending on how far along we've gone around the unit circle. Here we're going to have points along this hyperbola give us hyperbolic functions. Here, this is called the hyperbolic cosine. It's often abbreviated as cosh, C-O-S-H. H stands for hyperbolic, so hyperbolic cosine of x, comma, the hyperbolic sine of x is often abbreviated S-I-N-H and pronounced sinh. Yes, I know there's no C there. That's just the way it's pronounced. Cosh and sinh of x. Right? So we have that these functions are defined as points along this hyperbola, which is asymptotic to these lines and which passes through the point 1, 0. Now, even though we can define these points geometrically, and here we define them this, I'm defining them this way to show you where the name comes from. Namely, it comes from a hyperbola, the points of a hyperbola. We define our hyperbolic functions independent of a geometric interpretation, thankfully, because this geometry can be a little complicated from time to time. We're going to define them using the following definitions. The hyperbolic sine of x, also called the sinh of x, is equal to e to the power of x minus e to the power of minus x over 2. The cosh of x is defined by e to the power of x plus e to the power of minus x over 2. These definitions seem to come out of nowhere. You might say, what does that have to do with this? These are not exponential. They're what's a hyperbola? And what does that have to do with this? I mean, a hyperbola has, I guess, something to do with a circle. At least they're both conic sections. But what does this have to do with a circle? How does this have anything to do with the regular trig functions as we're used to them? The name for right now is just sort of, it's a familiar enough name because it's relating the points on one conic to some other points on a different conic. And the x value here is referred to as the cosine, so on the circle. So on the hyperbola, we're going to refer to it as the hyperbolic cosine. And likewise, the y value is on the circle is given by giving you the sine of t. So here on the hyperbola, the y value is giving you the hyperbolic sine of t. But again, what does that have to do with this relationship? What does that do with an exponential? For right now, we're going to say just don't worry about it, right? This actually will make more sense by the end of chapter 9. When we get to the end of chapter 9, you're going to realize that this definition not only makes a bit of sense here, but it also tells us why these are so closely related to each other. We're going to see here in a moment that the relationships between these go further than just the name. There's actually a lot of stuff that these have in common. And at the end of chapter 9, you'll learn exactly why. Not only that, but you'll learn what do exponential functions have to do with either of these. But for now, it's just, okay, here's how we're going to define them. And unfortunately, it's not something that makes complete sense until later, namely the end of chapter 9. We're going to define the hyperbolic tangent, often read as tanh. Yeah, I know, there's no C here, but I didn't make these names up. That's what they're called. The tanh of x is, it's going to be defined as the sinh of x over the cosh of x. So sinh of x over cosh of x. Okay, so that does sound like something that the trigonometric functions do, the circular functions. And here, since these are both defined in terms of exponentials, if you take this and divide by this, the 2's divide away, and you're left with e to the x minus e to the minus x over e to the x plus e to the minus x. And then we're going to take the reciprocals of these. We're going to name the reciprocal of the hyperbolic sine function. We're going to name it the hyperbolic cosecant function. And it's going to be named CSCH like that. Again, don't blame me for the names. These names have been around for a very long time. This is pronounced cosech. And yeah, it's not exactly a phonetic name. Cosech. Here, this is the reciprocal of the hyperbolic sine function. It's the reciprocal of sinh. 1 over sinh of x. And so you can define it as, just reciprocate this thing. You can define this as 2 over e to the x minus e to the minus x, although most people would just write it this way. Same thing with the hyperbolic tangent function with tanh. You can write it this way. Most people write it this way. So these are defined in terms of exponentials, and the rest are usually defined in terms of the first two. But if you want to, you can define all of them in terms of exponentials. Here we do have one stipulation. X should not equal to 0, because if x is equal to 0, that's 1 minus 1, which is 0. And dividing by 0 is kind of a no-no. So here we have the added stipulation that x should not equal to 0. The reciprocal of the hyperbolic cosine function, the reciprocal of cosh, is going to be the hyperbolic secant function, also called sech. That one almost makes sense, right? Sech. The hyperbolic secant function of x, that's going to be defined as the reciprocal of the hyperbolic cosine. It's going to be defined as the reciprocal of cosh. And, of course, that's the way most people define it. However, if you want to, you can define it in terms of the exponential. 2 over e to the x plus e to the minus x, if you like. Here, if both of these are, if x is equal to 0, 1 plus 1 is not 0, so we're okay with that. Here, x can equal to 0 if we like. And finally, the reciprocal of the hyperbolic tangent, the reciprocal of tanh, is the hyperbolic cotangent. Cotang, because that makes a lot of sense, right? Cotang is equal to 1 over the hyperbolic tangent over tanh of x, which again, most people would define it this way, but you can also define it in terms of the exponentials. E to the x plus e to the minus x over e to the x minus e to the minus x. And again, we want to make sure that's not 0, which means x should not equal to 0. Because again, 1 minus 1 would be a no-no in the denominator. Whenever we look at the hyperbolic functions, we will note that they do have a lot in common with the regular trigonometric functions for reasons that for now will remain a mystery. At the end of chapter 9, once you learn about Taylor expansions, those similarities will begin to make a lot more sense. We'll also learn a lot more about the trigonometric functions, which we don't know about yet, some things that we may not suspect. Namely, they are related to the exponential functions. All right. For now, we're going to give a single illustration of the similarities between the hyperbolic functions and the trigonometric functions. And that is, we're going to establish the fact that a very well-known identity is very similar between these two systems. So here I will ask you to recall the Pythagorean identity. Cosine squared of x plus sine squared of x is equal to 1. that's something that's hammered into you all the way since trigonometry, and it's used over and over again in pre-cal and cal 1. And we'll see it from time to time in cal 2 as well. The Pythagorean identity relates the sum of the squares of sine and cosine and tells you it's equal to 1. It turns out that we have something very similar for the hyperbolic functions. It turns out that cosh squared of x, now it's not going to be plus, these are not exactly the same. They're similar, but not exactly the same. It's going to turn out to be cosh squared of x minus sinh squared of x is equal to 1. We're going to prove that right here. So here, the proof of this. This is going to look an awful lot like something we did all the way back in trigonometry, and that was confirming the identities. You remember confirming the identities? We're going to do another example of that. We're going to rewrite this to express it in terms of other functions so that we can simplify to give us confirmation that this is in fact equal to 1. All right? So here, I hesitate to call this a full-on theorem, but sure, why not? Theorem. It's not a very important theorem. It's not anything very telling, but it is an example of why, or rather another example as to how these two are related to each other. So let's begin with this. Incidentally, in your homework, you'll have, I believe there's 3 of them, 3 identities you're going to prove. And anytime you prove an identity involving hyperbolic functions, they're all done the same way. Oops, there should be tanh squared of x. There we go. So cosh squared of x minus tanh squared of x. That's equal to, well, I know the definition of cosh. It's that right there. So that's e to the x plus e to the minus x over 2. And then that whole thing is being squared. Minus e to the x minus e to the minus x over 2. After all, that's the definition of sinh. And so, up here, that's the definition of sinh. And so that is what's being squared right here. All right, so let's do that. So now let's actually square this stuff out. The denominators are easy. 2 squared is 4. The numerators, well, I can square this out. E to the x plus e to the minus x squared. Well, when you square something, you multiply it times itself. So that's e to the x plus e to the minus x times itself. Just like that. And now we can distribute. E to the x times e to the x is equal to e to the 2x. Now you would add the powers together. E to the x times e to the minus x is e to the 0, which of course is just 1. Same thing here. E to the minus x times e to the x is again e to the 0, which would just be 1. And e to the minus x times e to the minus x is e to the minus 2x. Those will get added together. Here, 1 plus 1, well, that's going to give me 2. So my numerator is going to be e to the 2x. That's going to be e to the minus 2x. And then 1 plus 1 will give us 2. And then we can do the same thing for this numerator. And it'll work out the same way, except instead of having these be pluses, they'll be minuses. So here these will be minus as well. So the result will be e to the 2x plus e to the minus 2x. And then here that'll be a minus 2. So you can just distribute out the same way and you get this result. Okay, well now these have a common denominator. So I can merge them all together into one fraction. So that's all over 4. Well, notice e to the 2x minus e to the 2x is just 0. That's gone. E to the minus 2x minus e to the minus 2x, that's also 0. That's gone. That's all 0. 2 minus a minus 2. Okay, well, minus a minus is plus, so 2 plus 2 is 4. Oh, and now everything's gone except 4 over 4, which is, sure enough, the number 1, which concludes our proof. Anytime you're going to prove an identity for a hyperbolic function, it pretty much always works the same way. You're going to start off by writing off the definitions of the appropriate components, and then you're going to simplify using the exponential functions. So here, you might actually try one. Go ahead and give this a try. you're going to prove the following statement. Let's see. So you'll remember the sum and difference formulas from trigonometry, which stated that, let's see, that was this, let's go with the sine one. The sine of x plus y is equal to the sine of x times the cosine of y plus the cosine of x times the sine of y. And this is something that was established all the way back in trigonometry. And you even use this in Cal 1 to find the derivative of the sine function. Here, this is sine of x plus h over minus sine of x over h, the difference quotient. And then you use this formula to simplify. Right? So here, it's going to turn out that the hyperbolic sine has not just a similar result, but actually an identical result. So here, recall that this is true. This is not the thing you're trying to prove. This was proven years and years ago in trigonometry, whenever you might have taken that. Well, let's see. If you're in Cal 2 now, that would have been 3 semesters ago, so maybe 2 years ago. Years and years. That's 2 years, right? So here, go ahead and prove the following. And again, I'll call this a theorem. It's not really a very important theorem, and it's something that's central to what we're studying, but it is going to elucidate some of the properties of these hyperbolic functions as exponentials. Here, the hyperbolic sine of x plus y is equal to the hyperbolic sine of x times the hyperbolic cosine of y plus the hyperbolic cosine of x times the hyperbolic sine of y. Or using the abbreviations, sinh of x plus y is sinh of x cosh of y plus cosh of x sinh of y. All right? So you're going to go ahead and prove that this is true. I suggest you start from this side. It's generally easier to start with the more complicated side and simplify rather than to start with the simpler side and try to build it up. But it's up to you. Go ahead and give that a try. Pause the video and give yourself as much time as you need. And once you have a result, go ahead and unpause and we'll go through it together. All right, so let's take a look here. We're going to start off with these, and I'm just going to write out all their definitions. Here, I'm going to start off with sinh of x times cosh of y plus cosh of x sinh of y. Just like that. So now we can write sinh of x as being e to the x minus e to the minus x over 2. And cosh of x is e to the x plus e to the minus x. Oh, no, that should be y, right? Cosh of y. So e to the y plus e to the minus y over 2. Plus, all right, now I have cosh of x. So that's e to the x plus e to the minus x over 2. And then sinh of y, that's going to be e to the y minus e to the minus y over 2. All right, so sinh of x, cosh of y, cosh of x, sinh of y. So now let's start multiplying all these out. Now the denominators are easy. That's just 2 times 2 is 4. And same thing over here. 2 times 2 is 4. But now my numerators, well, let's see. I can distribute e to the x times e to the y. That's e to the x plus y. Right, when you multiply two things that have the same base, the powers add together. Same thing here. That's going to be e to the x minus y. So plus e to the x minus y. Here, that's going to be minus e to the y minus x minus e to the y minus x. And then here, that's a positive times a negative, so negative e to the minus x minus y. Just like that. And then on this side, same thing. E to the x times e to the y is e to the x plus y. E to the x times negative e to the minus y, that's going to be minus e to the x minus y. Multiply those together, that's plus e to the y minus x. And e to the minus x times negative e to the minus y. That'll be minus e to the minus x minus y. Okay. Notice now a few things subtract away. E to the x minus y plus negative e to the x minus y, that's just 0. And e to the y minus x plus negative e to the y minus x, that's also 0. Notice that these do not cancel out, they double up. That one with that one. E to the x plus y plus another e to the x plus y, that's 2e to the x plus y. And same thing for those. Minus e to the minus x minus y minus another e to the minus x minus y is minus 2e to the minus x minus y over 4. Now, of course, those can be reduced, right? Divide top and bottom by 2. That's going to give me e to the x plus y minus e to the x, minus x minus y over 2. Notice those both have a negative, so I can factor out a common negative. So I can write this as e to the x plus y minus e to the minus x plus y. I'm going to go ahead and put that one in parentheses as well, just to keep them both looking the same, over 2. Oh, but look, that is e to a power minus e to minus that power over 2. E to a power minus e to the minus power over 2. Oh, that's going to be the sinh of that power. Okay, so here that's going to be the sinh of that power. So we end up with the sinh of x plus y, which is what we were trying to prove. We're trying to get that if you start with all of this, sinh of x cosh of y plus cosh of x sinh of y, we end up with sinh of x plus y. And this confirms the sum formula for the sinh function is in fact analogous to the sum function for the sine function, the sum identity for the sine function. And this confirms your identity and concludes your proof. All right. So now that we've seen a few algebraic properties of these hyperbolic functions, let's look at some analytical ones. Let's look at some calculus. Right. Note that all of these functions are ones that we don't really need to worry about treating as new functions. You note that anytime we come up with a new function in terms of calculus, when we want to talk about it using calculus, we have to develop all sorts of new material for it. This is not the case here. Hyperbolic functions are really just regular exponential functions that are either being added or subtracted. That's what every hyperbolic function is. So here, we can develop all of the calculus of the hyperbolic functions by just looking and treating them as special cases of the exponential functions. We don't need any new material. We just treat them as exponentials. So here, you're going to note that just like the similarities between the trigonometric functions and the hyperbolic functions, as you see those algebraically, you're also going to see those in terms of calculus. So here, there's a theorem, and this one is a little bit bigger. The derivative with respect to x of the sinh of x is the cosh of x. You'll notice that a lot of these are going to be similar. Some of them will be identical, though not all of them. The derivative of sine of x is cosine of x. Oh, well, the derivative of hyperbolic sine of x is hyperbolic cosine of x. So that one's exactly the same. The next one is not exactly the same, although it is similar. The derivative of the cosine of x is the negative sine of x. That's not true for a hyperbolic function. You don't need a negative. The derivative of sinh of x is just cosh of x. The derivative with respect to x of the hyperbolic tangent function, the derivative of the tangent of x is secant of x. Oh, sorry, derivative of tangent of x is secant squared of x. Here it's going to remain the same. It's going to be the hyperbolic secant squared of x. The derivative with respect to x of the cotangent of x is going to be negative cosec squared of x. So that one will look identical to the way you remember the derivative of the cotangent function, just hyperbolic now. the derivative with respect to x of the sech function, the hyperbolic secant, is going to be almost the same as you remember from regular trigonometry. The derivative of the secant of x is the secant of x times the tangent of x. Here it's almost exactly the same. It's the negative thereof. So it's going to be the negative hyperbolic secant of x times the hyperbolic tangent of x. And the derivative with respect to x of cosec of x is going to be negative cosec of x times cotangent of x. So you notice these are all either identical to the ones you remember from trigonometry, or the difference is they have a negative or are missing a negative where the other one would have had one. Of course, if these values are not x, if they're a function u of x, then of course you can always use the chain rule. So here the derivative of sinh of x is cosh of x. The derivative of sinh of u would be cosh of u times u prime. All right, so you can always use the chain rule. Likewise, antiderivatives are still the same. If the derivative of sinh is cosh, the antiderivative of cosh is sinh. All right, so if this is the derivative, going in the opposite direction, you have antiderivatives. All right, so here, we could also write this as the antiderivative of cosh of x dx is equal to the sinh of x plus a constant of integration. And likewise for this one, the derivative of cosh of x is sinh of x, so the antiderivative of sinh of x dx is equal to the cosh of x plus a constant of integration. Here, the derivative of the tangent of x is sech squared of x. So that means that the integral of sech squared of x is going to be the tangent of x. Here the integral of the cosec squared of x dx is equal to, well, the negative's got to go somewhere, so negative cotangent of x, forgetting my constants of integration, plus c. Here the integral of sech of x tangent of x dx, that's going to equal to, again, the negative's got to go somewhere, negative sech of x plus our constant of integration. And finally, the integral of cosec of x cotangent of x is equal to negative cosec of x plus our constant of integration. All right. So here, let's, I'm going to go ahead and prove just one of them, because again, just like all of the other properties of these hyperbolic functions, you can prove all of them the same way using the definition, using the exponential definition. So here I'll go ahead and prove it for, let's use this one. So a very partial proof. In fact, just one out of all of these six. Once you prove this one's automatic, right? So here, partial proof, very partial. We're going to take the derivative with respect to x of the cosh of x, which is, by definition, the derivative of e to the x plus e to the minus x over 2. Okay. Well, that's a constant 1/2, right? 1/2 times this, which we can then factor out because, of course, the derivative is a linear operation. So we can go ahead and write this as 1/2 times d dx of e to the x plus e to the minus x. Okay, well, that's going to be 1/2 times. We can take the derivative of each of these on their own. After all, the derivative is a linear operation. So that's the derivative of e to the x plus the derivative of e to the minus x. Oh, but we know how to do both of those. That's 1/2 times. The derivative of e to the x is just e to the x again, plus the derivative of e to the minus x is e to the minus x. Oh, but now because of the chain rule, I have to multiply times a -1. So times -1 times the derivative of negative x. So putting that together, that's going to be e to the x That's now negative, so we can just write that as minus e to the minus x. And then everything's being divided by 2. Oh, but by definition, that is the hyperbolic sine of x. So here that's going to be the hyperbolic sine, the sinh of x, which confirms that the derivative of cosh is sinh. Derivative of cosh is sinh. All the other ones are done exactly the same way. You start off with this expression on the left, write it in terms of the exponential, take the derivative, and then realize, oh yeah, that gives you the thing on the right. And then, of course, all of these are equivalent to all of those. So let's take a look at some examples of using this. So, for example, let's say you want to find the derivative with respect to x of the tanh of 4x squared plus 3x. Okay. Well, we see that the derivative of tanh of x is sec squared of x. Oh yeah, but this is not just x. It's a function of x. Okay, so we're going to have to use the chain rule. So the derivative of tanh of something is sec of something, or rather sec squared of something. Oh, but now because of the chain rule, I now need to multiply this times the derivative of this. Like that. Oh, okay, but the derivative of that is simple. The derivative of a polynomial. So here we're left with what? 8x plus 3 times sec squared of 4x squared plus 3x. And there we go. An antiderivative will work in pretty much the same way. What we want to do is we want to use how we already know how to take antiderivatives, namely through substitution and basic formulas, and now use that using our new hyperbolic functions and their derivatives as we know them. So here we take the cosh of the square root of x over the square root of x. Like this. Note that this is the cosh of something. So here we're going to want to use substitution. Whenever you have a composition, substitution is to integrals the way the chain rule is to differentials, to derivatives. So here we're going to take u to be the argument of cosh, square root of x, and so du is going to be 1 over 2 root x dx, which you'll notice is almost exactly what we have here. Dx over square root of x. Dx over square root of x. Oh, but we don't have that 2. Okay, so multiply both sides by 2. That becomes 2 du, and now here, that 2 goes away, leaving us 1 over root x dx. So by our substitution, that's now the integral cosh of u, cosh of u, and now dx over square root of x, that's just 2 du. So the 2 is a constant, which we can factor out of the integral. 2 du. And now that is something we know how to do. The antiderivative of the cosh of u is the sinh of u. One of the nice things about cosh and sinh is that their derivatives and antiderivatives don't ever have a negative. So with trigonometric functions, sometimes it's a little tricky to remember, okay, which one has a negative, which one has a positive? Here, they're all positive. So here, 2 times the integral of the cosh of u is just 2 times the sinh of u, plus a constant of integration. And of course, u is the square root of x, so we just plug that in. So 2 sinh of the square root of x plus a constant of integration. And that's our result. Just like that. All right, now we've defined a new category of functions, the hyperbolic functions. Well, anytime you define a new category of functions, you typically follow that up by defining its inverse. We define the trigonometric functions, do the calculus with the trigonometric functions, and then we proceed to talk about the inverse trigonometric functions. We define the logarithmic functions, and then we proceed to talk about the exponential functions. Well, now here we have hyperbolic functions, so let's talk about the inverse hyperbolic functions. Note that the hyperbolic functions are all defined in terms of an exponential. So it should come as no surprise to learn that the inverse of the hyperbolic functions will be written as the inverse of the exponentials. Or in other words, they'll be written as logarithms. So here we're going to define the inverse hyperbolic functions, and they're all going to be logarithms. So let's take the inverse hyperbolic sine function, and that's defined as the natural log of x plus the square root of x squared plus 1. And the domain of this is all real numbers. The reason we state that is because not every one of these will have an infinite domain. So here the domain is all real numbers. The inverse hyperbolic cosine function, the cosh inverse of x, is defined as the natural log of, and this looks almost exactly the same. The difference is this very last plus is going to be a minus. This one, however, is not defined for all real numbers. It's only defined from 1 and above, starting at 1 and above. Note if you did use 0, that would be 0 plus the square root of negative 1. And that's the natural log of I, natural log of an imaginary number. Can that be done? Actually, it can. But it's not something we're prepared to do now. This calculus course restricts everything to the calculus of real numbers. Imaginary numbers, we actually can use calculus using complex variables, but that's a whole other subject. The theory of analysis of complex variables is, it's not Cal 2 or Cal 3. It's something in a different field. If you use a number that's very negative, though, okay, well, that'll be positive, but that'll be negative. And when you combine them, you end up with the natural log of a negative. And if you remember the graph of the natural logarithm, it only accepts arguments that are positive. So here, it's not that you end up with an imaginary number, but if I use x equals to negative 20, this thing right here will be a negative number, which doesn't belong to the arguments of a logarithm. Actually, that's not quite true. You can take the logarithm of a negative, but again, it involves complex numbers, which is something we're going to avoid here. At the very end of chapter 9, there's going to be one exception to that. We're going to talk just a little bit about complex numbers, but that's mostly as a specialized example. For the most part in this course, we deal with only real valued functions. Okay? The inverse hyperbolic tangent, the inverse tanh, is defined as 1/2 times the natural log of 1 plus x over 1 minus x. And here, this is defined only in the interval from -1 to 1, and it doesn't include either of those endpoints. For the same reasons, here, if we have values outside of this interval, you end up with either logarithm of 0, which is undefined, logarithms of negatives, which, again, require complex analysis, require the calculus of complex numbers, which is not what this course is about. The inverse hyperbolic cotangent function, cotang inverse of x, looks almost exactly the same here. The only difference is that your terms here are flipped around. So this is going to be 1/2 the natural log of, instead of 1 minus x, this one's x minus 1 in the denominator. Here you could leave that alone, but just to make it look like that one, you could write 1 plus x, but usually it's written as x plus 1, just to make it look the same as the denominator. Here, the domain is everything except that, from negative infinity up to -1, union with everything from 1 to infinity. The inverse hyperbolic secant function, sech inverse of x, that one's going to be given by the natural log of 1 plus the square root of 1 minus x squared all over x. Well, actually, I shouldn't say all over x because it doesn't include the natural logarithm. It's just the argument is all over x. And here the domain of this is from 0 to 1, not including 0, because obviously dividing by 0 is undefined, but it does include 1. And finally, the inverse hyperbolic cosecant function, that's a mouthful, isn't it? Cosec inverse of x. is equal to the natural log of 1 over x plus the square root of 1 minus x squared. No, that's for that one. So it should be 1 plus x squared over the absolute value of x, like that. And this one's defined everywhere except at the point 0. Because again, dividing by 0 is kind of a no-no, yeah? So invert the hyperbolic cosecant, and that is valid at all numbers except for 0. Okay. So here's how we define them. The derivation of these is sort of long and drawn out. Before I started the lecture, I actually went through and did the computation on my own just to see what it would look like. And yeah, you can do that. You can start with the exponential function that looks like this and say, okay, so now let's invert using the tricks that you learned in algebra. Just say, okay, y is equal to e to the x minus e to the minus x over 2. And then say, okay, now the inverse function would be x equals e to the y minus e to the minus y over 2. Okay, now solve for y. And that's perfectly doable, and oh my goodness, it's very, very long. So here, I'm not going to go through the derivation of these because, yes, it's doable, and it's doable by the techniques that you would learn in an algebra class. But my word, it's a very long process. So here, instead of doing that, what I'm going to say is you can confirm these simply by the definition of the inverse function. Building this formula is a long, somewhat drawn-out process, but confirming this is literally just using the definition of what we mean by an inverse. Remember, the inverse hyperbolic sign is the inverse hyperbolic sign because when composed with this function, should have all operations simplify out, and we should just be left with x at the end. So if we plug one of these functions into the other of these functions, everything should cancel out, and you're left with x at the end. So here, instead of deriving these, which is complicated, I'm going to simply confirm one of these is the correct one. So confirming that this definition of, and I'm just going to go ahead and pick inverse hyperbolic sign of sinh inverse of x is correct. Or let's just say is valid. So what do? You take one and plug it into the other. So I'm going to take sinh of, I guess I'll start with the inverse one. And I'm going to plug that into the original one. I guess given what I said, I wrote that backwards. I'm going to take sinh, and into sinh, I'm going to plug in the inverse sinh. Like this. Okay, well, I know what both of those are. So that's sinh of the inverse hyperbolic sign. Well, we just defined it as the natural log of x plus the square root of x squared plus 1. And that's just this one right here. That was my definition. Okay, so now I'm going to take the sinh, and I'm going to plug this into it. Now remember, sinh can be written as e to a power, which is going to be the argument, like that, minus e to minus that power, divided by 2. Okay, so now here, note that these two simplify out. E to the natural log of this just gives you this. All right, exponentials and logarithms are inverses. So here we can write this as x plus the square root of x squared plus 1, just like that. Here, remember we have a property of logarithms that tells us that if you have a constant on the outside, it can be brought up as a coefficient. It can be brought up as a coefficient. That coefficient can be brought up as a power. So here that's a minus 1. So let me write that as minus 1. And that coefficient can be brought up as a power right here. So now you have e to the natural log of this to the minus 1. And since the exponential and the logarithm are inverse operations, we're just left with x plus the square root of x squared plus 1 to the minus 1. So there's minus x plus square root of x squared plus 1 to the minus 1. And all of that is over 2, which in order to save some space, I'm going to say, okay, all of this is being multiplied by a half. That's the same thing as saying dividing by 2, yeah? All right, so now negative 1, well, that means that this is going to be reciprocated. So I can write this as 1/2 times x plus square root of x squared plus 1. I'm going to leave some space there because I'm going to write something in a moment. Minus 1 over x plus square root of x squared plus 1. All right, that's what a negative 1 means. It means you're going to reciprocate this. And now I can add these together, or I guess I should say I can subtract these by giving them a common denominator. So I can multiply top and bottom here by that denominator. So that's going to be x plus square root of x squared plus 1, so that they have the same denominator. And then I can do the same thing on top up here. X plus square root of x squared plus 1, just like that. So now this is going to give us a common denominator. So that's going to be 1 over 2 times x plus the square root of x squared plus 1. All I've done is I've factored out the common denominator out here. So now let's simplify this stuff in here. This stuff in here is, let's see, x times x is x squared. X times square root of x squared plus 1. That's going to be plus x root x squared plus 1. And then again, so plus another x root x squared plus 1. And then if I multiply these, that's going to be square root of x squared plus 1 times itself. Or in other words, square root of x squared plus 1 squared. And that square and that square root together will just give us the radicand, x squared plus 1. And then don't forget you have a minus 1 over here. So all of that was all of this. And then don't forget you still have a minus 1 out there. So now some stuff will combine and simplify. Notice that 1 and minus 1 go away. And some of these come together. X squared plus another x squared. Well, that's 2x squared. And x root x squared plus 1 plus another x root x squared plus 1 will give us 2x root x squared plus 1. And everything else is gone. All of that is going to be over 2 times x plus root x squared plus 1. Notice that in that numerator, I have a common factor of 2x. Both of these have a 2 in them. Both of them have an x. So I'm going to write that as 2x times, once I factor out the 2x, that leaves me just an x, plus, that leaves me just the root of x squared plus 1. And then my denominator is still that common denominator of 2 times x plus root x squared plus 1. And now those divide and those divide, which leaves us just the value of x. So you note that that means that if you compose these two functions, as the same as composing these two functions, everything reduces down to the identity function. So what that means is that the sinh of the sinh inverse of x, these two just go away and you're just left with x. So in a way, these two undo each other, which is what inverse functions are supposed to do. So that is equal to x, which by definition, the definition of what inverse functions are, which by definition of inverse functions confirms that what we defined as sinh inverse, which confirms that the natural log of x plus the square root of x squared plus 1 is the inverse of the sinh of x. That confirms that that's true. Again, this doesn't show you how this was developed. That can be done. In fact, it's strictly algebraic. The procedure of going through that is just very, very messy. Incidentally, you can do the same procedure if you have a mind to. You could confirm that any of these are true the same way. You could take this and plug it into this one. Oh, sorry. You could take this and plug it into the hyperbolic cosine. You can take this one and plug it into the hyperbolic tangent, and really any of these. And in the end, they'll all give you just the identity function. They'll all give you x. So that would confirm that any of them are correct, or that all of them are correct. So now the question remains, okay, I developed a hyperbolic function. I defined it. Well, actually, I said that backwards. I first defined a hyperbolic set of functions, and then I developed them. I developed a few properties of them, and then I developed how we find a derivative and an antiderivative. Okay, well, now we've defined inverse hyperbolic functions. Okay, well, then the next step would be to define some of their properties. In particular, since this is a calculus class, let's talk about how to find the derivatives and the antiderivatives. So here we go. Theorem. Let's see here. The derivative with respect to x of the inverse sinh of x is equal to 1 over the square root of x squared plus 1. Notice another similarity between this and the trigonometric functions. You'll recall from a previous section that the derivative of the inverse sine function, also called the arc sine, looks very similar to this, where in fact the difference was, instead of this being 1 plus x squared, it was 1 minus x squared. But otherwise, that looks very, very similar to what we had before. So this is just another example of showing how the hyperbolic functions and the regular trigonometric functions, the circular functions, continue to have things in common. Let's see here, the derivative with respect to x of the hyperbolic cosine function, the inverse hyperbolic cosine function. That's going to give us, again, something that looks very familiar. It's going to equal to 1 over the square root of x squared minus 1. Again, if this is something other than x, if you have this or this as being a function of x, you could always just use the chain rule. So you would say, okay, 1 over square root of u squared plus 1 times the derivative of u. Okay? And we can talk about the derivative of the inverse hyperbolic tangent function. At this point, you notice me saying the names very slowly because there's so many pieces, I'm having a hard time keeping them straight. The inverse hyperbolic tangent of x. That's going to equal to, you'll remember that for the inverse tangent function, for the arctangent, our derivative was 1 over 1 plus x squared. Now it's going to be 1 over 1 minus x squared. And again, if you have a function u here, that would just be 1 over 1 minus u squared times u prime, times the derivative of u. Now, one thing to note is that the derivative of the inverse hyperbolic cotangent function is going to look exactly the same. Now, you might say, okay, well, if it looks exactly the same, how is that possible? You have two different functions that have the same derivative? I didn't know that could happen. Well, they're not exactly the same. You'll remember that when we define the inverse functions, the inverse hyperbolic functions, there is a restriction of the domains. Even though the expressions work out to be the same for both, the difference is that this one's only valid when x is between minus 1 and 1, whereas here it's only valid outside of the interval between minus 1 and 1. So here, this one's the case for whenever x is less than 1 in absolute value, whereas this one is the case only when the absolute value of x is greater than or equal to 1. I guess I shouldn't say equal to 1, because if it's equal to 1, that's undefined, right? So here, that's absolute value of x is greater than 1. So that's the difference. Even though they have the same result, the expressions look the same, these are valid at different times. This one's valid only when the absolute value of x is less than 1, whereas this one is only valid when the absolute value of x is greater than 1. The derivative with respect to x of, oh, let's see, which one are we missing? Well, let's see, tangent, cotangent. So that's going to be the inverse hyperbolic secant function, sec inverse of x. And if you take the derivative of sec inverse of x, you get negative 1 over x square root of 1 minus x squared. Okay. And over here, if you take the derivative with respect to x of the inverse hyperbolic cosecant function, sec inverse of x, that's going to give us minus 1 over the absolute value of u. Oh, sorry, absolute value of x. Square root of 1 plus x squared. Note that this also brings us the opposite direction, namely if the derivative of this is that, then the antiderivative of that would be this. So here we can write those, and here, just like with the inverse circular functions, the inverse trig functions, we don't use all of them because some of them are similar to each other so that we can actually double them up and say, oh, look, these belong together as a pair rather than have 6 different ones. Because of the fact that these are defined with respect to a logarithmic function, the natural log of something, the natural log of something else, here, although we can write this is equal to this, it's often useful to write it in terms of the more basic logarithmic function, partially because it's simpler for people to work with because you're more familiar with a logarithmic function, but also because some of the signs here, the pluses or the minuses, can be manipulated to make some of the expressions a little more forgiving, meaning if it doesn't look exactly like this, we might be able to change the plus or the minus here. So the way these results end up are, if you take the antiderivative of, if you take the antiderivative of du over the square root of u squared, either plus or minus a squared, depending on the plus or minus here, you'll have a different plus or minus in your result. That's going to equal to the natural log. It's either going to be the cosh or the sinh. You'll notice that these two look very much the same. You have square root of variable squared, either plus or minus constant squared. Okay, so it's either going to be cosh or sinh inverse, cosh inverse or sinh inverse. Oh, well, the difference between the definition of those two, if you look at the definition of cosh inverse and sinh inverse, that plus or that minus is the only difference. So here you can write this as the natural log of u plus square root of u, and again, it's either going to be plus or minus, oh, that should be u squared, plus or minus a squared. And then, of course, since you're taking an integral, that's plus a constant of integration. So if this is a plus, that's a plus. If that's a minus, that's a minus. These come directly from these here. Again, the reason we write them with a logarithm instead of a sinh and cosh is because, again, first of all, it's probably simpler for most people to work with logarithms than these new functions, but also because here, these two look very different. But if you write them in terms of the logarithm, the only difference is either that plus or that minus, which makes it easier to summarize the result. Hey, if that's a plus, that's a plus. If that's a minus, that's a minus. Which is simpler than saying if that's a plus, we have to deal with inverse hyperbolic sine, and if that's a minus, we have to deal with inverse hyperbolic cosine. Plus is plus, minus is minus. Okay. We have another pairing. Sinh and cosh go together. Tangent and cotangent will also go together, but we're going to write them in terms of the logarithm, which will make it a little bit simpler. Du over a squared minus u squared. Okay, well, that looks like it's going to be tangent, cotangent. Looks like those two. That's going to be 1 over 2a times the natural log of the absolute value of a plus u over a minus u plus a constant of integration. Again, notice how similar those look to the inverse trig functions. If this was a plus instead of a minus, we'd be dealing with the inverse tangent function, the arctangent. But with a minus, now we're dealing with the inverse hyperbolic tangent. Okay? And the third one is, let's see if I can get that one in here, the integral of du over u times the square root of a squared and either plus or minus u squared, and now that'll be these two. We're going to end up with having that equal to negative 1 over a times the natural log of a plus the square root of either a squared plus or minus u squared. And again, if that's a plus, that's a plus. If that's a minus, that's a minus. Over the absolute value of u, plus some constant of integration. And again, these results are not proven on their own. Once you have these are automatic, as long as you can write these in terms of their logarithmic definitions. All right? So here, the only ones that you really would go out of your way to prove would be these. These come from just rewriting these in terms of logarithms. So here, the proof of this, just like I have been doing for most of this section, I'm going to go ahead and prove one of them, because again, all of the proofs are pretty much done the same way. The details will change, but the structure is the same. So let me go ahead and prove just one of them. So I'll just do that very first one that we had. Let's go ahead and prove, what was the first one we did? We had the derivative of the inverse sinh function. All right, so let's go and do that one. We want d dx of sinh inverse of x. Okay, well, we know the definition of the sinh inverse of x, and thankfully that definition is a very nice one that we know how to work with. We know a lot about logarithms. So let's take the derivative of the natural log of x plus the square root of x squared plus 1. That's the definition of the inverse sinh, or that. So taking the derivative of that is the inverse of the derivative of that. These are identical. Okay, well, I know how to take the derivative of a logarithm. Let's go ahead and recall. That if you want to take the derivative with respect to x of the natural log of some function of x, the natural log of u of x, that's going to equal to u prime of x over u of x. All right? The derivative of the natural log of u is u prime over u. So here, and that's just a recall, that's just sort of a little extra side note. So this is going to equal to, okay, well, the derivative of the natural log of that is the derivative of that over that. Okay, so that's going to be d dx of x plus the square root of x squared plus 1 over x plus the square root of x squared plus 1. Just like that. So now we have to worry about taking the derivative of the numerator. That numerator is something we know how to take the derivative of since Cal 1. The derivative of x with respect to x is 1. The derivative of, with respect to x of the square root of this function is going to be 1 over 2 times the square root of that function. All right, the derivative of the square root of something is 1 over 2 root something. But now because of the chain rule, we now have to multiply by the derivative of the inside. So that's going to give us the derivative of x squared, which is just 2x. Okay, so that's the derivative of x. That's the derivative of that square root of x squared plus 1. And all of that is getting divided by x plus the square root of x squared plus 1. All right, so now let's start simplifying. First of all, you'll notice that those 2's divide away. And you'll notice that I can combine these as long as I give them a common denominator. And since that's the number 1, the common denominator is very easy to create. You just multiply top and bottom by that other denominator. So now we have the square root of x squared plus 1. Right here, that's that numerator. Plus Here I have 1 times x, which is just x, over my common denominator, which is the square root of x squared plus 1. Now, of course, all that's getting divided by this other denominator, x plus the square root of x squared plus 1. Oh, look, those are the same. Okay, the order is a little different, but those are the same. I could rewrite that as x plus the square root of x squared plus 1. Addition's commutative, so I can just flip those around. Square root of x squared plus 1. And then dividing by that expression is the same as multiplying by the reciprocal of that expression. So instead of dividing by x plus that square root, I'll multiply by 1 over x plus that square root. Oh yeah, but now those divide away. Since these are identical to each other, a number divided into itself is 1. So here we're left with 1 times 1 as our numerator, which is 1. And our denominator is 1 times the square root of x squared plus 1, which is the square root of x squared plus 1, which is exactly what I wanted. The derivative of the inverse sinh of x is 1 over the square root of x squared plus 1. 1 over the square root of x squared plus 1. So the derivative with respect to x of sinh inverse of x is equal to 1 over the square root of x squared plus 1. And that confirms our result. As part of your assignment, your part of the homework here, you're going to see, I believe, the proof of, I want to say it's finding the derivative of the inverse hyperbolic cosine, or maybe it's the inverse hyperbolic secant. You're going to see one of those at least in your homework. Note here that because that is a function, if you want to replace that value of x with another function of x, the chain rule would apply. So note, all of these other ones would work the same way. If I wanted to take the derivative with respect to x of the sinh inverse of u of x, well, that's still going to be the same result. That's 1 over the square root of u squared plus 1. Oh, but now because of the chain rule, I would have to multiply by the derivative of that u prime of x, which most people would write as u prime over the square root of u squared plus 1. So keep in mind that these results that we can prove are all with respect to x, but keep in mind that things like the chain rule, the product rule, the quotient rule, they haven't gone anywhere. So here we confirm, or rather we prove one of our parts of our theorem, and in your homework you'll prove at least one other one. Although you will note they are all pretty much the same. Take the derivative of your function. Okay, we'll write it in terms of a logarithm, and I'll take the derivative of the logarithm and simplify. So let's go ahead and give that a try. In fact, here's the formula for not just the derivative with respect to x, but a derivative of a composition of a function inside of a hyperbolic sign. So give this a try. Let's have you do the derivative with respect to x of the sinh inverse of the tangent of x. Notice it's going to follow this exact pattern with your function u being the tangent of x. Go ahead and pause the video and go through it. And once you are done, go ahead and unpause and we'll go through it together. All right, so let's take a look. We're taking the derivative of the inverse hyperbolic sine of a function. Well, that's going to be equal to 1 over the square root of that function squared. So that's tangent squared of x plus 1 times the derivative of that function, derivative of tangent of x, which is secant squared of x. Just like that. Note this can now be simplified. We can write this together as secant squared of x over the square root of the tangent squared of x plus 1, which we can now write as secant squared of x. Now note, this is a positive value. If you square something, It's going to be positive. So since that's a positive number, I can simply write it as the square root of the square of that expression. Here, that square and that square root would cancel out, and you'd have no problem with positives or negatives since that's positive anyway. All over the square root of tangent squared of x plus 1, which you note now that's a radical in the numerator and the radical in the denominator. We can write this as the radical of secant squared of x quantity squared over tangent squared of x plus 1. But now that's a Pythagorean identity. Tangent squared of x plus 1, that's secant squared of x. So we can now write this as the square root of the secant squared of x squared. And here, in fact, I'm going to write it as secant squared of x times secant squared of x. Squared means times itself. Over, that's now secant squared of x. And now these two divide away, and I'm left with the square root of secant squared of x. Now you might be tempted to say, okay, well now that's just secant of x. Well, not quite, because remember, secant of x can be positive or negative. Okay, so then squaring it would completely make everything positive, and then the positive square root would keep it positive. So here, if secant of x is already positive, then yeah, the square and the square root go away and you're just left with secant of x. But for those cases where secant of x is negative, squaring it would make it positive. Okay, so then this is secant of x, but just always positive. Okay, so then the absolute value of the secant of x. And that's our result. So the derivative with respect to x of the inverse hyperbolic sine of the tangent of x is the absolute value of the secant of x. And that makes us happy. Note the secant of x would be incorrect because I would assume you have negative values sometimes. Here, squaring it makes everything positive. All right, so now for our last example, let's take a look at using one of these results. Instead of looking at a derivative, let's take a look at an antiderivative. All right, so for our example, let's consider finding the integral of x over 9 minus x to the fourth dx. Okay. Now note here we have the difference of two squares. It might not look like it because x to the fourth is definitely not a square, except that it's the square of x squared. So here we might make it a little bit simpler if we use a substitution. We can say u is equal to x squared, which means du is equal to 2x dx. Oh, well, that's x dx right there. So I just need that extra 2. Okay, well, let me go ahead and divide both sides by 2. And that way I get 1/2 du is equal to x dx. Okay, so now that's exactly that. So here this is going to become the integral. That x dx, that's 1/2 du. That 1/2 comes out. Du over 9 minus, well, if u is equal to x squared, then x to the fourth is just u squared. Right? Here, if I square both sides, that's going to give me u squared is equal to x squared squared, or in other words, x to the fourth. So that's going to be u squared. I can write that in a slightly more telling way by writing this as 1/2 integral of du over 3 squared minus u squared. If you think back to a previous section, that almost looks like the inverse tangent. Well, yeah, but the inverse tangent is the sum of these, not the difference. Oh, okay, but seeing as how closely related the trigonometric functions and the hyperbolic functions are, you can probably guess what's coming next. Oh, okay, instead of having the sum of a constant squared minus plus a variable squared, now we have a difference. Constant squared minus variable squared. Oh, and there it is, constant squared minus variable squared. So here this is going to be an arctangent, or sorry, an inverse hyperbolic tangent. But here, instead of writing it in this form, we tend to write all of those in terms of the natural logarithm. So here we're going to write that as 1/2 times, we're going to have 1 over 2a. where again a is the constant that's being squared. So let me write that as 2a, 2 times 3, times the natural log of the absolute value of a plus u over a minus u, plus some constant of integration. Now, of course, all that multiplies together, so that's just 1 over 12. 1 over 12. There we go. 1 over 12 times the natural log of the absolute value of 3 plus. Now, of course, u is a stand-in for x squared, so let's go and pop that back in. Oh, sorry, squared, right? Squared. There we go. Plus a constant of integration. So that gives us our result. We're not going to go very far in depth to hyperbolic functions. There's some other stuff we could do if we had a mind to, but here we're going to stop with this. The hyperbolic functions, we defined them. We talked about how to relate them to the circular functions, the trigonometric functions, and we saw how to work with them algebraically. Basically, you just write them in terms of the exponential. Then we defined their inverses using a logarithm, which is natural given that the originals were exponentials. And so we then found how to take derivatives and some simple antiderivatives that involved both the hyperbolic functions and the inverse hyperbolic functions, which of course here we see as natural logarithms. All right, so that brings us to the end of our section. If anybody has any questions, comments, or problems, please make a note of those and reach out to me during office hours or during our next meeting. And I hope everyone has a nice day.